Hello, students. Today we are going to explore a very interesting and practical topic, the uses of aldehydes and ketones. Let's begin. Now, have you ever really thought about this? I'm sure you have seen it in your school biology lab. A frog or some other specimen floating in a jar. How does it stay so perfectly preserved for years and years without decaying? Well, I can tell you, it's not magic. It is pure chemistry. And the secret lies with the very compounds we are studying today. So we're going to see that our world is, in many ways, built by these chemicals. But why is it important to study their uses? It's because this is where the theory from your textbook really meets the real world. When you understand the applications, you'll see exactly why this chemistry matters. At the simplest level, I want you to think of aldehydes and ketones as versatile molecular tools. Just like a mechanic has a toolbox with different spanners and screwdrivers for different jobs, chemists use these compounds for a huge range of tasks. And this versatility comes from their unique chemical structure. So, what makes these tools so special? It comes down to three key properties. First is their reactivity. They have something called a carbonyl group. That's a carbon double bonded to an oxygen. And this group is always ready to react and form new bonds. Second is their polarity. The charge difference in that C connected to O bond makes them excellent at dissolving other substances. And third, their volatility, which means they can evaporate easily. This is very useful for things like solvents and perfume. The main point here is that we are not just memorizing some facts. We are going to see how these fundamental properties directly lead to real-world impact. We are here to answer that big question that every student asks. Why does this chemistry actually matter outside the textbook? To really understand this, let's take a tour of an imaginary chemical factory. We can walk through different departments and see our molecular tools, the aldehydes and ketones, hard at work. Okay, our first stop is the resins and plastics department. Here, the star worker is formaldehyde, a simple aldehyde. When it reacts with another chemical called phenol, it produces baculite. Now, this was one of the very first synthetic plastics ever made, and it is incredibly tough and heat-resistant. You can still find it in old electrical switches and the handles of kitchen utensils. Let's move to the next department, solvents. The key player here is a ketone that I'm sure you all know, acetone. Because of its polarity, which we just discussed, acetone is a fantastic solvent. It can dissolve things that water cannot, like paints, resins, and of course, as you know, it is the main ingredient in nail polish remover. Now for a much more fragrant stop on our tour, the perfumes and flavors department. Many aldehydes have very distinct and often pleasant smells. For instance, benzaldehyde is what gives almonds their characteristic scent, and cinnamic aldehyde is responsible for the warm, lovely aroma of cinnamon. Our final stop is the biology and preservation department, and this is truly fascinating. Aldehydes play a dual role here, almost like they have two different personalities. Inside our own bodies, glucose, which is a type of aldehyde, is the fuel for life. But that same family of chemicals in the form of formalin is used to do the complete opposite, to stop all biological processes and preserve specimens perfectly. So, we have completed our factory tour. Now, let's zoom in on a couple of these examples to see the chemistry in action and connect what happens in the lab to what happens in your life. Let's go back to our perfectly preserved frog. What is the secret? Well, it's a solution called formalin, which is formaldehyde in water. The highly reactive formaldehyde molecule attaches itself to the proteins in the frog's tissues, especially the amino groups. It creates a vast network of connections, or crosslinks, almost like a chemical net. This makes the proteins rigid and completely stops the process of decay. Now, this same kind of thinking is vital in the pharmaceutical industry, where purity is everything. Acetone is a perfect tool here. A newly synthesized drug can be dissolved in acetone, separating it from any impurities which do not dissolve. Then, because acetone is so volatile, it can be easily evaporated, and what is left behind? The pure crystalline drug. This is a critical step in making safe and effective medicines. So now that we have seen these specific examples, let's zoom out again to understand the true scale of their importance. And I think this might surprise you a little bit. You know, you might think that these compounds, formaldehyde and acetone, are just some common chemicals you find in a school lab bottle. But in reality, they are pillars of the global chemical industry. They are massive industrial giants, produced on an enormous scale. Just consider this number, not thousands, not even millions, but billions of tons of formaldehyde are produced every single year. And this is not just for preserving a few lab specimens. It is the industrial backbone for countless products we use every day, from the resins in our furniture and plywood to fabrics and plastics. All right, let's quickly recap the key points for your exam. Number 1, always think of them as versatile molecular tools. Number 2, keep in mind the mental image of the chemical factory with different departments. And number 3, remember a key example, like how formalin preserves a specimen or how acetone is used as a solvent. If you can just hold on to these 3 simple ideas, the versatile tools, the busy factory, and one solid real-world example, I can promise you this entire topic will feel much more manageable and much lighter when you are preparing for your exams. So I will leave you with this final thought. From now on, when you flick on a light switch made of bakelite or smell a perfume with a specific fragrance, I hope you will take a moment to think about the invisible but essential world of aldehydes and ketones that made it all possible.